Welcome back to another explainer. I am absolutely thrilled to have you here today. Take a second and just think about the ground you're standing on, or sitting above, right now. It feels pretty permanent, right? Solid, unmoving, deeply reliable. But the crazy truth is that seemingly solid ground beneath our feet is actually a dynamic, relentlessly moving machine. Today, we're going to break down the anatomy of Earth's engine, jumping straight into a massive achievement of modern geology, plate tectonic theory.
Let's take a quick look at our roadmap. We're going to start with Earth's broken shell, then move through divergent, convergent, and transform boundaries, check out the driving forces behind it all, and finally wrap up with how this literally shapes life on Earth.
All right, Section 1, Earth's broken outer shell.
So, to really understand our planet, we've got to toss out the idea that the Earth is just wrapped up in a single, unbroken sphere of rock. Actually, it's cracked into roughly 15 major pieces, along with a bunch of smaller ones. We call these tectonic plates, and they are in a state of slow but absolutely constant motion. The boundaries where these 15 major pieces meet, well, those are the most geologically active places on our entire planet.
When we're talking about these plates, we're really talking about the lithosphere. That's Earth's rigid outer layer. It includes all of the crust, whether that's under the oceans or under the continents, plus the uppermost, coolest part of the mantle underneath. Now it's solid and it's super brittle. It ranges from just about 10 kilometers thick under the mid-ocean ridges to over 200 kilometers thick under the oldest parts of our continents. And because it's so brittle, when stress builds up, this layer cracks and snaps. And, as you might guess, when it snaps, we get earthquakes.
But what's really fascinating here is the sheer contrast with the layer sitting directly below it, the asthenosphere. This is the partially molten upper mantle. Try to think of it like warm modeling clay. It's not totally liquid, but it's hot enough to behave plastically. If you push on it long enough, it just kind of deforms and flows. And this warm, flowing clay is exactly the thing that allows those rigid, incredibly heavy lithosphere plates to literally float and glide right on top of it.
Moving right along, Section 2, Divergent Boundaries or Pulling Plates Apart.
This is essentially the first of 3 different gears in our giant Earth engine. At a divergent boundary, 2 plates are actively separating. As they pull apart, a massive gap opens up, and hot mantle material rushes up to fill that void. This rising material partially melts, and as that magma cools and solidifies, boom, it forms brand new crust. So as these massive plates pull away from each other at a rate of roughly 1 to 15 centimeters a year, the Earth is quite literally creating new real estate. Brand new lithospheres being born right there.
Now what's brilliant is how this pulling apart looks totally different depending on where it actually happens. When this divergence happens underwater, it creates these massive mid-ocean ridges, like the Mid-Atlantic Ridge, where new oceanic crust is continuously shoving the plates apart. But when it happens on land, right beneath the continent, it stretches and thins the crust all the way out, creating a long, narrow depression called a rift valley. The East African Rift Valley is absolutely the most famous example of this. The African plate is slowly splitting into 2 pieces as we speak. If this keeps up for millions of years, the whole continent will completely split, ocean water will come flooding in, and a brand new ocean basin will be born. How wild is that?
Next up, Section 3, Convergent Boundaries, crashing plates together.
Okay, so when these massive plates shift from pulling apart to crashing directly into one another, a collision is totally inevitable. But the fallout depends entirely on what kind of crust is colliding. We've basically got 3 incredibly violent scenarios here. First, oceanic meets continental. The denser oceanic plate gets violently forced beneath the lighter continental plate in a process called subduction. That descending plate sinks down into the mantle to be recycled, which carves out a wildly deep ocean trench. Fun fact, the Mariana Trench, literally the deepest point on Earth, is one of these subduction trenches. This whole process also triggers melting above it, creating massive land volcanoes like the Andes. Okay, scenario 2, oceanic meets oceanic. Here, the older, cooler, denser plate subducts under the younger one. Again, this carves a deep trench, but those volcanic eruptions eventually build a whole chain of islands right out of the ocean, called an island arc. Think Japan or the Aleutian Islands. Finally, scenario 3, continental meets continental. In this case, both plates are way too buoyant, too low in density to actually sink, so neither one subducts. Instead, they just completely crumple, fold, and thicken, pushing rock massively upward to form towering mountain ranges.
The absolutely crucial takeaway here is the sheer scale of time and force involved in that last scenario. Just wrap your head around the number 50 million.
The Indian plate has been smashing head-on into the Eurasian plate for 50 million years. This is a massive, continent-sized crumpling effect that created the Himalayan mountains, the tallest peaks on Earth. And get this, because that collision is still ongoing right now, those mountains are literally still being pushed higher today.
That brings us to Section 4, Transform Boundaries, grinding plates past each other.
So this is the third and final type of boundary, and the mechanics of a transform boundary are terrifyingly simple. Plates slide horizontally past each other along a massive fracture known as a fault. Now at this boundary, no new crust is created and no old crust is destroyed. But the catch is, rock surfaces are incredibly rough. They definitely don't just glide smoothly past one another. As the plates try to move, they get stuck. Immense kinetic energy and stress just build and build along the fault line until finally, the rock simply breaks and slips. And when it does, it releases all that pent-up energy in the form of a violent earthquake.
To ground this concept in reality, just look right at California. The San Andreas Fault is without a doubt the world's most famous transform boundary. This specific sliding motion, where the Pacific plate is grinding northwestward right past the North American plate, is the exact mechanism responsible for California's frequent and very famous earthquakes.
Let's shift gears to Section 5, the forces driving plates.
Up to now, we know how they move at the boundaries, but we really need to uncover the hidden engine room of the planet to understand exactly why they move. Ask yourself this: what kind of invisible forces are actually powerful enough to push and pull entirely rigid, massive rocks, we're talking entire continents, across the surface of the Earth? Just try to imagine the sheer amount of energy required to make that happen.
While modern geophysics identifies three main heat-powered mechanisms driving our planetary engine. First up is mantle convection. Basically, hot rock deep in the mantle rises, spreads out right beneath the lithosphere, cools off, and then sinks back down. This slow, circular flow exerts a physical drag on the bottom of the tectonic plates, essentially pushing them along. Second, we have ridge push. Over at those mid-ocean ridges where brand new crust is formed, the rock is hot, expanded, and elevated. Gravity simply grabs hold of this elevated material, pulling it downward and outward, which pushes the plate away from the ridge. And third, slab pull. At those subduction zones we talked about, the cold, incredibly dense edge of a sinking plate drops into the mantle under its own weight, pulling the entire rest of the plate down behind it. It's super fascinating to note that most geophysicists today actually consider this slab pull to be the single most dominant driving force for plate motion.
Let's actually look at the data on plate speeds, because while all three of these forces work together, their mix varies a ton depending on where you are. Take the Pacific plate, for example. It's surrounded by subduction zones on several sides, meaning it gets a whole lot of that slab pull. Because of that, it practically races along at a relatively fast speed of up to 10 centimeters a year. On the flip side, look at the African plate. It really lacks those sinking, pulling edges, so it just slowly creeps along at a sluggish 2 centimeters per year.
And finally, Section 6, Shaping Life on Earth.
Let's bring this all together now. It is absolutely crucial to realize that plate tectonics doesn't just shape rocks, mountains, and oceans. It literally shapes the history of life itself. Think about it. When these massive continental landmasses drift apart over millions of years, populations of organisms that used to be connected are suddenly separated by these huge, uncrossable, newly formed oceans. Because they become completely isolated from one another, these animal populations are forced into entirely unique, independent evolutionary paths. This produces entirely new species that are found absolutely nowhere else on the planet.
And honestly, there's no better example of this than Australia's wildly unique wildlife. Bizarre and wonderful marsupials like kangaroos, koalas, and platypuses, they only exist today because the continent of Australia physically broke away from Antarctica and other landmasses tens of millions of years ago. Plate tectonics essentially turned Australia into this isolated evolutionary laboratory, locking it away from the rest of the changing world.
Which leads us perfectly to one final, mind-expanding thought. We've seen exactly how the engine works, and we've seen how it separated the continents to create the world as we know it today. But remember, the engine hasn't stopped. If the ground beneath our feet is in a state of constant, slow-motion reshuffling, what is Earth and the incredible species living on it going to look like 50 million years from now? I really want you to think about that. Thank you so much for joining me for this explainer today. I hope it completely changed the way you look at the solid ground beneath your feet. Keep learning, keep questioning, and I'll catch you next time.